you know what heat is. Heat is a measure of energy for us. You might call it calories. You might have heard BTUs before in your life. But for us, the SI unit, like the SI standard unit, is called the joule. And there's joules and kilojoules. A kilojoule is 1,000 joules. And then there's calories, little c calories. And just so you know, the little c calorie, big C calories is really 1,000 little c calories. It's a kilocalorie. And we use it for food. So anytime we use a big C calories, it's for 1 kilogram of water. How much energy does it take to make it go up 1 degree Celsius? If you gain that much heat, it goes up 1 degree Celsius. If you lose that much heat, it'll go down 1 degree Celsius. We use it for food because, after all, 1 kilogram of water is not very much, right? So then, a BTU is what's called a British thermal unit. And British thermal units, this guy right here, they are a standard from a long time ago. And the only thing that you see in these today are like air conditioners, heaters, ovens, stoves, charcoal grills or gas grills, things that you would cook with like that. They're still rated in BTUs, how much energy they put out. And you can imagine where the word British thermal unit came from. Just so that you know, 1 little C calorie is equal to that many joules. All right? So that's a good start. Specific heat is just what it says right here. You guys can get this in your notes. And the symbol is C sub P. I don't know why. It's kind of crazy, but that's what it is. And every different material, water, steel, copper, concrete, has its own separate specific heat. Just like everything's got a different melting point or everything's got a different formula, then everything will have its own specific heat, unique to that material. Right? And here's a couple that you can see right here. You notice that water's got a huge heat capacity or specific heat compared to other things. All right, let's see if you guys can figure out the difference. Make a guess in your head. Say it out loud. If you guessed that the one on the left was full of gasoline, you're wrong. If you guessed instead that the one on the right is full of water and the one on the left has no water in it, then you would be exactly right, because the water in the one on the right is keeping it from boiling, and the one on fire on the left caught fire very, very quickly. The heat got absorbed into the paper hot enough to make it burn. The one on the right, the heat is going into the paper but then into the water. And the only thing that's actually burning, if you look at it, is the very, very tip. And that very tip is dark because there's no water there. It's all paper. All right, so this is specific heat again, remember, is equal to the Q, and that is the heat in joules or in calories over the grams times the change in temperature. Okay, and that's kind of spelled out here. So to find specific heat, we need to know the amount of heat absorbed or lost, how much the temperature went up or down. That's what this triangle means, is change in temperature. Anytime you guys see that delta sign, that's a sign that temperature is changing or something's changing. All right? Calorimetry then is how do we measure with a meter calories or joules or whatever. But just like a pedometer is a meter that measures your steps, a speedometer is a meter that measures your speed. A calorimeter is a meter or a measurement device that measures your calories. So this is what you need for one. Now you can have this kind of thing. In addition to the sample, you have something to start it. That's what this coil is, starts it. You fill this thing full of oxygen. So the oxygen comes down this hole. In an oxygen-rich environment, most anything will burn. So you put a sample of food or something like that. This is called a bomb calorimeter because basically you're going to burn this whole thing. Then you also have a jacket of water around it, and this water, its job is going to be to absorb the energy. So you know the mass of the water, you know the starting temperature of the water, because that's what this is. You know water specific heat. This is a stirrer, and very, very fancy. But what it does is the food burns, the energy goes into the water, and as the energy goes into the water gets hotter. And all you have to do is watch the thermometer, and you can tell how much the temperature goes up. As the heat goes into the water's going to get warmer, and from that you can solve for Q. So we can go back to this thing right here, and we can solve for Q, or how many calories or joules are given off when that food burns. Now that's a fancy one. This is probably several $1,000s. This is a $15,000 one. It'll do it automatically for you. All you have to do is put the sample in, press go, and the little computer thing does it. We don't have $15,000. I don't have several $100s. I do have this though. All you need is a styrofoam cup, a lid, a thermometer, because what can you do? You can put water in the styrofoam cup. You can use the thermometer to measure the temperature change, and there you have it, a calorimeter. So, when we do calorimetry, we follow this law called the law of conservation of energy. Meaning, energy can't just disappear. Whatever energy you have in the system has to go somewhere. So, the water, right here, the Q of the water is the energy absorbed by the water. All we have to know is how much the temperature of the water goes up, the mass of the water, and this constant over here. The object, therefore, if we know the mass of the object and the change in temperature of an object and the specific heat of an object, we can know the Q of the object. These two Q's have to be equal, because if the object loses heat, then the water will gain heat. So you can figure out sometimes the mass of an object. If you know the Q and you want to find the mass, you can find that. Last thing I want to show you real quick is about density. And density is just very, very simple. Mass per unit volume, grams per cubic meter, grams per liter, grams per milliliter, kilograms per cubic centimeter. As long as you have some unit of mass over some unit of volume, then you're good to go. All right, so what I wanted to show you is how you use this equation here and what this pyramid of power means. So if you're looking for density, all you do is take your finger, hold it up to the screen, and cover this up. Now, what is the math? Mass divided by volume. That was pretty easy. All right, well, let's say you were looking for mass. Let's say you knew density and you knew volume and you're looking for mass. Put your finger over the screen, cover that up, and what is it? Density times volume. Density times volume. And since you know density times volume, you can find the mass. You can do this for all kinds of equations. You can make yourself what's called a pyramid of power. All right? I knew it was mass over volume. So mass on top, volume on the bottom. Density goes in the other spot.